Hello there, and in this video we're going to continue our discussion of moment-generating functions for discrete random variables. So recall the definition of a moment-generating function m. So m, x of some parameter t, is defined to be equal to the expectation of the random variable e to the t x, which can be found explicitly through the Taylor series of the exponential function, or can be given by the summation across all values of x, that is in the domain of the random variable x, of e to the tx times the probability mass function evaluated at the variable x of interest. So we've already proven that if x is a geometric random variable, then its probability mass function, p of x, is equal to 1 minus p to the x minus 1 times p, where p is the probability of success. Here, the support of the function is the interval 1 to infinity. And from this value, we computed the moment-generating function for x, and we found it to be equal to p e to the t divided by 1 minus e to the t times p minus 1. From this moment-generating function, we were able to develop the mean, the second moment, and the variance of the distribution. We found that the mean of the random variable, if x is geometric, is equal to 1 divided by the probability of success. We found the second moment of x to be equal to 2 minus p divided by p squared. And from those two, we were able to prove that the variance of a geometric random variable is just equal to 1 minus p over p squared. We're going to continue this process, but look at two other random variables, the binomial distribution and the Poisson distribution. So now let's assume that x is binomial. So if x is binomial, then its probability mass function is given to be the combination of n choose x times 1 minus p to the m minus x times p to the x, where n is the possible number of Bernoulli trials. So the support of this probability mass function is the interval 0 to n. So let's derive the moment generating function for this random variable. So mx of t is by definition equal to the sum across all values of x, which is x is equal to 0 to m, of e to the tx times the probability mass function. So that's going to be n choose x times 1 minus p to the m minus x times p to the x. I'm going to slightly rearrange this expression. I'm going to rewrite this as the summation from x is equal to 0 to n. I'll write my binomial coefficient first, so n of x. I'm going to write my etx and px together. And I'm going to rewrite 1 minus p to the m minus x as 1 minus p to the m divided by 1 minus p to the x. Actually, that is not necessary. We can just rewrite this as 1 minus p to the m minus x. So I'm going to combine these two things since they're both have an x exponent in them. So this is just going to be the summation from x is equal to 0 to m of n choose x of e to the t times p, all raised to the x, times 1 minus p to the n minus x. I'm going to define two things to make this obvious. I'm going to let a be equal to e to the t, p. I'm going to let b be equal to 1 minus p. So this expression is equivalent to writing the sum from x is equal to 0 to n of n choose x of a to the x times b to the m minus x. So you should be able to recognize this expression. This is equivalently a plus b to the m. This is what people refer to as the binomial theorem. So I'm just going to replace a and b back into this expression. So this is going to be equal to e to the t times p plus 1 minus p all raised to the n. So this is the moment generating function for the binomial random variable. So now I'm going to differentiate this function with respect to t. So m prime of x of t. So by the chain rule, this is going to be equal to n times e to the t p plus 1 minus p raised to the m minus 1 times the derivative of the inside, which is just going to be equal to p e to the t. So if this is true, I can evaluate this as 0. so m prime x of 0, which is equivalently the first moment of the random variable, is going to be equal to n times e to the 0 p plus 1 minus p to the m minus 1 times p times 1. So that's just going to be equal to n times, so e to the 0 is 1, and then p cancels with that p there, so we're just left with 1 times m minus 1 times p. So 1 to any power is going to be 1, so this is just going to be equal to np. So therefore, the expectation of a binomial random variable is just equal to np. Now I'm going to find my second derivative. So the second derivative of x with respect to t is going to be equal to the derivative of respect to t of this expression. And I'm going to rewrite it as npet times etp plus 1 minus p m minus 1. So this is a product of two functions, u and v. So I'll use a product rule here. So it's going to be the first times the derivative of the second. So the second derivative is going to be m minus 1 times etp plus 1 minus p to the m minus 2 times pet, that's the derivative of that inside. So first derivative second plus the second, so etp plus 1 minus p m minus 1 times the derivative of the first. So the derivative of npet is just going to be itself, npet. I'm not going to simplify this because I'm just going to plug in 0 for this. So m double prime x of 0, which is equivalently the second moment of x, is going to be equal to what? So e to the t is going to go to 1, so we're just going to be left with np there. So we have this m minus 1 hanging out. So e to the t is going to go to 1, and p minus p is going to be 0. So we have just 1 inside this parenthesis, and 1 to the m minus 2 is just 1. And then e to the t is going to go to 1, so we have a p left there. So this is the first expression. Plus, so e to the t is going to go to 1 again, and p minus p is 0, plus 1 is 1, and 1 to the m minus 1 is just going to be 1. And then over here we have np times 1, which is just going to be equal to np. So let's rewrite this in a nicer way. So the second moment of x is going to be equal to, so we have np times p, that's going to be equal to np squared times m minus 1 plus np. So we can distribute this over, so we're just going to have n squared p squared minus mp squared plus np. So that is the second moment of the binomial random variable. And we've already found that the first moment is equal to np. So now let us find the variance. So remember that the variance is going to be equal to the second moment minus the first moment squared. So the second moment we already know is n squared p squared minus np squared plus np minus np, the quantity squared. So that's n squared p squared minus mp squared plus np minus n squared p squared. So notice that the np squareds will cancel, and we're just going to be left with np minus np, the quantity squared. I can factor out np out of both of these, so I'm going to have np times 1 minus p, and this is the variance of the binomial random variable. So that is everything that's important about the binomial distribution. Now let us go through the properties of the Poisson distribution, and we'll do that in the upcoming video.